In order for a collision to be good, molecules have to collide with each other with enough energy to break the bonds that need to be broken for the reaction to take place. And this energy, this minimum energy that is necessary to break these bonds and to lead to a good collision, is called the activation energy. The activation energy is given the symbol E, capital E, with the subscript lowercase a. And we will define it as the minimum energy that is needed for a good collision. We can find the activation energy on a reaction energy diagram. So we haven't really looked at reaction energy diagrams for quite a while. We're going to draw two side by side. Reaction energy diagrams are a graph of the energy of a reaction over a period of time as the reaction goes from reactants to products in an exothermic reaction or an endothermic reaction. And so we've looked at these diagrams before, and in the past when we've looked at them, we've always looked at them in the context of the change in energy for the reaction overall, the difference in energy between the reactants and the products. And we talked about things like this is an exothermic reaction because the products are lower in energy. The products are lower in energy than the reactants. The products over here are higher in energy than the reactants, so this would be an endothermic reaction. The amount of energy that it takes to go from the reactants up to this high point on the energy diagram is the activation energy. So this amount right here is the activation energy, the minimum energy that it takes for us to get up here to the high point on the energy diagram. And it doesn't matter if it's exothermic or endothermic, the difference in energy between the reactants and the high point, so where can I draw that? The difference in energy between the reactants and the highest point on the graph is the activation energy. The high points on the graph up here is the transition state. The transition state is given a symbol that looks kind of like an equal sign almost with a vertical line through it. So this point right here is the transition state. The transition state is I don't really know what to call it. It's not a reactant and it's not a product. It's something that exists as the molecule is switching from reactant to product. So the transition state is our high energy it is not isolatable, meaning that we can't stop the reaction when we reach the transition state. So because we can't stop it there, we don't ever really see these transition states. They're not detectable. They only exist for a very brief amount of time. They are these things that exist as bonds are breaking or forming or a little bit of both. When we try to draw pictures of transition states, they usually look really funny. So like if we go back up to this reaction that I drew up here when I was trying to illustrate a good collision and the alignment of the oxygen relative to the bromine to get a good collision. The transition state for this reaction would look something like this. So the hydrogens, which are not affected by this reaction at all, are on the molecule unchanged. I've kind of moved their position a little bit, but not by much. And the carbon-bromine bond is breaking while the carbon-oxygen bond is being formed. And so it kind of looks for a little while like this carbon atom has 5 bonds on it, which it doesn't. It has 3 real bonds and then a bond that's breaking and another bond that's being made. And putting it in square brackets and putting the symbol for transition state up in the corner is pretty standard notation to kind of indicate that this is what we think that the structure looks like as the molecule moves from reactant to product. So the activation energy is related to the rate constant for a reaction through this equation called the Arrhenius equation. Arrhenius is a really hard word to spell. Arrhenius equation. The Arrhenius equation has 2 forms to it. One form is K equals capital A E, this is the mathematical E, to the negative E sub A over RT. So that's one version of the Arrhenius equation. The other is a natural log version of that same equation. The natural log of the rate constant K is equal to the natural log of A minus E sub A over RT. And we'll mostly use it in the natural log form, but I mean, you might see it in either form. So let's write down what these variables are. K, that's the little k, that's our rate constant. The capital A is a new constant for us, and it goes by 2 different names. Some sources call it the frequency factor. The frequency factor is a constant that's specific to a reaction. So every time you solve a problem with the Arrhenius equation, you're going to have to be given the value of A for that particular reaction. And it has to do with, the frequency of the collisions. So sometimes it's called the frequency factor. Sometimes it's called the pre-exponential factor, because it comes before the exponent. E sub A is the activation energy. And again, the Arrhenius equation is really all about tying K and E sub A together, like giving us a mathematical relationship between the two. The standard units for activation energy are kilojoules per mole. R in this equation is our gas constant. And in this equation, because this is a thermodynamics thing, we want it in terms of 8.3145 joules per mole Kelvin. And you got to look out here because you are going to be combining E sub A and R together in this equation. You've got to watch the units. You're going to have to convert units, because your joules and kilojoules are incompatible. And then last but not least, T is the temperature in Kelvin. And so for the most part, solving problems with the Arrhenius equation is really as simple as just plugging stuff in to the equation. So I'm going to show you another form of the Arrhenius equation that we will use quite a bit. If we want to calculate the change to the rate constant with a change in temperature. So this would be like, let's say that we did a reaction at a specific temperature and we measured K. for that temperature. And then we wanted to know if we changed the temperature to something else, what would K be? So if we wanted to calculate or look at the comparison of two different temperatures and two different rate constants, we could use another version of the Arrhenius equation that allows us to combine these multiple K's and T's together. And that's going to be the natural log of one of the K's divided by the other K. So I'm going to call one K1 and the other one K2. And it doesn't have to be like an initial or a final or anything. And that's going to be equal to E sub A over R times T1 minus T2 over T1 T2. And so for this, all that we have to do is worry about making sure that we're combining the correct K with the correct T. So K1 and T1 would be a rate constant and a temperature. So this would be the rate constant at temperature T1. They're connected to each other. And then K2 and T2 would be the rate constant for that particular temperature. The rate constant at T2. And, because I know that you love math as much as I love math, we could totally derive a relationship between these two equations. Where does this K1, K2 equation come from? I'm not going to walk you through the whole entire derivation because I know I'm not a dummy. I know you're just going to fast forward it. You're not going to watch it. You don't love math as much as I do. The equation, I'm just going to show you where it comes from, so don't fast forward yet. So it comes from taking two Arrhenius equations. We're just going to put a 1 on everything. K1, A1, EA1, R1, T1, and K2, A2, EA2, R2, T2. And what we end up doing is combining these two equations together by by subtracting them from each other, basically. So the natural log of K1 minus the natural log of K2 equals the natural log of A1 minus EA over EA1 R1 T1 minus ln A2 minus EA2 over R2 T2. And so once we get here, things start simplifying because A1 and A is just a constant. So A1 is equal to A2, just like R1 is equal to R2. And EA1, the activation energy, is equal to EA2, the activation energy. So with those equalities, this equation starts simplifying down real fast, and you use some properties of logs, and you do some amazing math, and then you end up with this equation right here, which we will practice using.